Okay, so we'll continue our discussion on unsteady viscous flows. So in the last lecture, we looked at a problem of an impulsively pulled plate. So you had one boundary which was moving with a constant velocity starting at time t equals 0. So there was an impulsively set into motion, and the fluid that was resting on that boundary extended all the way to infinity. So we solved the unsteady momentum equation with the assumptions basically being that we are looking at rectilinear flows, flow which is also two-dimensional. So we end up with an equation which bears similarity to heat conduction equation. And then for this particular problem that we did, we had no inherent length scales or time scales that were there in the problem. So there was a velocity with which I dragged the plate. The plate is infinitely long. And because the plate is infinitely long and you are doing this impulsive motion, you are not introducing any length or time scales in the problem. So then we used a dimensional analysis in order to argue that the non-dimensional velocity, because you are solving here for a linear differential equation with linear boundary condition. So if I scale the velocity by the plate velocity, then the governing solution that you would get would be only a function of the spatial coordinate y, the temporal coordinate t, and the kinematic viscosity nu. And then since the left hand side is a dimensionless object, the right hand side should also be a dimensionless object, and then based on dimensional considerations we find that it has an argument of something that goes as y by square root nu t. And for consideration of simplifying algebra, we have this factor of half. But the important aspect being that there is this new variable that we have, which depends both on space and time. That's the similarity variable, which reduces my PDE to an ODE. So we arrived at this particular ODE, and then on solving that particular ODE, we are able to actually obtain what the solution is expressed in terms of the coordinate eta, which is y by 2 square root nu t. So z here is the dummy variable, it's not the spatial coordinate z, it is just an integration variable that we have here. And we realize that the more than actually the mathematical approach of using a similarity variable and reducing this equation, an interesting aspect in this particular problem is that emergence of a length scale, which is the viscous length scale. So we have a length scale in this problem which goes as square root of nu t. So when you say that I have an object, so I'll just draw some arbitrary object, and now this object is moving with a velocity u, and then you suddenly accelerate or decelerate this object, and the object now starts to move with a velocity, let's say 2u. So there is a change in the boundary condition. There is a change in your forcing in the problem. Now, how quickly will the fluid respond to this? That is the question. Now, if you think of potential flow, in potential flow it's instantaneous, because in potential flow you are solving for del square phi equal to 0 subject to the boundary condition that u dot n or dou phi dou n is equal to whatever is u bar dot n. So if you make, and this u bar is actually a function of time. So if you suddenly move the cylinder twice as fast, you do this as a jerky motion, there is no modification to the flow that captures this particular history. Obviously, the force is going to be cognizant about it because the force has a rate of change of potential. So if you are now saying that there is a certain change in u of t, we learnt about added mass and we realized that that acceleration is responsible for a reaction from the fluid on the object. So there is an added mass component to it. But the potential that we solved, that potential for any problem, for any configuration, is only dependent on the instantaneous velocity of the object. You do a change, the velocity field that you obtain will be exactly related to the velocity at that point in time. It doesn't care, the potential doesn't care what was the velocity at an earlier instant of time. So if I were to plot u bar as a function of t, let's say this is the velocity of the object as a function of time. Let's say initially it was moving with 1 meter per second. And then I give it a jerky motion and it goes to 2 meter per second at some time interval, let's say 1 second. I do a next set of experiment where I will start from 1 meter per second, but then at 0.5 seconds I will use a ramp, and the ramp is going to approach 2 meter per second over some interval of time. Let's say it achieves 2 meter per second at 1.2 seconds. Now, if I am looking at the problem at 2 seconds interval, both the protocol of how I change the velocity of the object are now going to tell us that the body is moving with 2 meter per second. At this particular instant, the velocity field in the two problems are identical. It is not really aware of the fact that you arrived at this 2 meter per second velocity using very different mechanism. Like you can have all kinds of possibilities, right? You can do something like this. And all these protocols would give you exactly the same velocity field at 2 seconds. There is no difference. This is what potential flow tells us. Because there is no effect of viscosity in this problem, so it is going to be instantaneously responding to whatever is your boundary condition. Now, what we have learned is that there is something called as a viscous length scale, which means when you have the body's motion changing, there will be a zone around the body that scales as square root nu t, so that is order nu t, within which the effect of modification of the boundary condition is felt. So momentum is basically diffusing from the boundary, which is why I am constantly appealing to this idea. Just think of it like dye. Think of it like dye or some ink that you have released in water. So that's going to diffuse and spread. Similarly, momentum also diffuses and spreads in the fluid. So the region over which momentum, the information of change of momentum has percolated will scale as square root nu t. So if you wait long enough, the entire fluid would have realized that there is a modification to the boundary condition. This is obviously an argument which is a scaling argument. There is no precise region in the domain. It's not like in the flow you have drawn an external circle or a sphere and you are saying that the flow is different inside this and outside that region. This is for our understanding. This is for our understanding that the aspect of momentum diffusion, just like the spreading of dye, has made its presence felt, which is increasing as square root nu t. So as time evolves, that region basically starts to become larger and larger. So this is the key part of the unsteady problem that we need to understand. That in unsteady problem, you are actually getting an information regarding the influence of moving boundaries as they change. So we had the accelerating problem. So in the accelerating problem, we saw that if we plot the velocity, so this is u by u bar, so this is 1 at the plate. So obviously at any instant of time, you will have a profile something like this. But then if you plot it for different instants of time, the difference being that as you evolve in time and you say that where do I find the fluid moving with, let's say 99% of the plate velocity. So if that's your question, that where do you have u, so u of y star is equal to 0.99 of u bar. What is that y star? What is that location? So you can find that location. And this location y star is going to grow as square root nu t. Now instead of 99, you can say some other number. This is just to actually make this point clear that if you were to draw a line here, that region as you are looking at where do you achieve that velocity at a later instant in time, that's going to increase because of viscous diffusion. And how it increases, it goes as square root nu t. Now, this problem of momentum diffusion, when we learned earlier about, we were starting to learn about kinematics, I mentioned this fact that vorticity is also a very economical way of understanding a problem. So they are kind of go hand in hand. So certain problems you can understand as momentum transport, but you can also have an equivalent interpretation in terms of vorticity transport. So for this particular problem, we are doing a 2D problem. And if you write down your 2D vorticity equation, your 2D vorticity equation will be dou t of omega z plus u dou omega z dou x plus v dou omega z dou y plus the kinematic viscosity equal to kinematic viscosity dou square omega z dou x square dou square omega z dou y square. Now we are looking at a problem that is two-dimensional and rectilinear. So there is only one velocity component u and that doesn't vary along x. So all these terms I can drop, and what I am left with is a vorticity equation that is dou omega z dou t is equal to nu dou square omega z dou y square. So we looked at momentum equation. You can now also see vorticity also has the same diffusion equation. So you can imagine in terms of diffusion of momentum, or you can also imagine it in terms of diffusion of vorticity. So now how do you think of in terms of diffusion of vorticity? Your initial condition is u at y equals 0 for any time that is greater than 0 is equal to u bar, right? And u for all y at t equals 0 is equal to 0. Which means if you want to write this mathematically, that there is an impulse that is provided at t equals 0. You have an impulse that is given at t equals 0. Your u at t equals 0 for all y. So this is y which is away from the plate. Y plus. Y plus is any point away from the plate, because at the plate there is a jump. At t equals 0, you gave it a pull. You tugged the plate, you made the plate move. So there is a sudden impulse that you have given at the plate. So at time t equals 0, the entire fluid is at rest and the plate has suddenly been brought into state of motion. Immediately at the next state, the layers which are sticking to the plate will start to move. But if exactly at t equals 0, I want to describe the velocity, that is going to be u bar. So I want to give it as a mathematical expression which is also including the plate. So if I want to include the plate, then I will write it as Heaviside function of minus y. So a Heaviside function h of x as a function of x will pick a value that is positive if x is positive. If x is negative, it will be 0. So it's a step function. I just have a step function here. So here I have, okay, so this I've given as minus y, right? So this should just be h of y. No, hang on, sorry. Because the fluid is at rest for all positive values of y. So there is a discontinuity that you have for the fluid velocity. The plate is in motion and the fluid is at rest. Now if you want to write down the vorticity corresponding to this, omega z of y at t equals 0, you will write this as minus dou u bar dou y. There is no v in the problem. So you are just going to have minus dou u bar dou y, which will be u bar, and the derivative of a Heaviside function will be a Dirac delta function. So the initial vorticity that you have in the problem is basically a Dirac delta function that you have. So now what do you have in this problem? You have a problem where initially you are giving at t equals 0 a vorticity that is confined only at a particular location. Obviously, we are not solving for y less than 0. In this particular case, we are not in the plate problem. We don't treat what is happening below the plate. But in this configuration, whether you see it below or above the plate, you have a layer or you have a sheet where vorticity is defined. So you have learnt of vortex lines. Vortex lines are basically at a given point. This is a vortex sheet. So you can think of at every point, if I draw the tip of the vortex lines, there are vortex lines that are coming out of the plane. So you take a lot of vortex lines like thread and you have stitched them and made it into a piece of fabric or a cloth, which is why this is a sheet. So the sheet basically has lines which are coming out of the plane. So this is a stack of sheets which are put on a line. So now when you have this vortex sheet, you are asking how does this equation evolve this particular vortex sheet. So you can solve this again using different techniques that you have. So if you write down what is your omega z y comma t, that's basically solving for the heat equation. That's solving for the heat equation with an initial source term that you have in the problem. So there are different methods of solving this problem. You can use transform, or this effectively is what is also known as the Green's function for the heat equation. So this is your evolution of vorticity. Now if you go back to what you had as a solution previously, this was your velocity field. Now try computing the vorticity field. What would be the vorticity field corresponding to this? So we found ux by u bar was 1 minus 2 by root pi eta 0 exponential of minus z square dz, where eta was y by 2 root nu t. So now if you compute your vorticity is minus du dy. So that is minus u bar of minus 2 by root pi d eta dy exponential of minus eta square. So if you work this out, you will have 2 by root pi d eta dy is y 1 by 2 root nu t exponential of minus y square by 4 nu t. So 2 and 2 are going to cancel out and you will get the same solution. So there is another way of thinking of this particular problem. You can think of this problem as momentum being diffused from the plate to the fluid. You can also think of this problem as diffusion of a vortex sheet. And this then becomes quite interesting because you don't need to necessarily think of this as an impulsively pulled plate problem. You can also think of this as a problem where consider that there is a stream that is coming in. There is some stream that is basically entering, and you have a boundary or a separating plate between the fluid below. And just for keeping it simple, I will say that the velocity on the top is initially u bar and the velocity in the bottom is 0. So there is a stream that is coming in, there is a plate which is there, and now the bottom fluid is at rest. Now the plate terminates. Once the plate terminates, what you are going to have is a fast moving stream moving with u bar and a quiescent stream which is at rest. Now if this was an inviscid problem, then they can coexist. I have two layers of fluid, one layer moving with velocity u bar and the other layer is at rest. Now you can always have them move with different velocities. You can have maybe this moving with u1 and this moving with u2, but I'm chosen for keeping it simple, the bottom being at rest. So the point is you have two co-moving streams moving with different velocities. Now what is the vorticity in this problem? If you just try to calculate the vorticity for this configuration, the top layer is uniform stream, which means vorticity is 0. Bottom layer is either quiescent or moving with different velocity. So here also vorticity is 0. But the vorticity at the interface between the two layers is non-zero, because the fluid velocity which is moving in the x direction has a discontinuity. It is jumping from one velocity to the other velocity over 0 thickness, which means that there is vorticity at that particular region, and this vorticity, if it was u1, would basically be u1 delta of y. If the bottom was moving with velocity u2, then it would be u1 minus u2 delta of y. So there is vorticity at the interface between the two streams. And now you can think of what you have done for the impulsively pulled plate problem as being applied here. That I have two streams of fluid which are moving with different speeds. Because of viscous diffusion, the faster moving fluid will want to drag the slower moving fluid. So if you plot the velocity at different instants of time, so let me just clear a little bit. Yeah. So let's try to sketch what the velocity will look like at different intervals of time. So initially, the velocity has a discontinuity. So the top layer is moving with some velocity, bottom is at rest. Now the layer which is at this interface, the stack of book example, you can think of like all the fluid being basically like stacks of books. So the stack of the book which is on the top layer and the book which is just below that layer, they will try to drag each other. The bottom one was at rest, the top one is moving. So obviously they don't like having a relative motion. Relative motion is what viscosity would like to resist. So the moment there is a resistance to relative motion, the consequence is the top one gets slightly slowed and the bottom one gets slightly sped up. So the bottom one was earlier at rest. So here the top and bottom, I am just saying a layer here and a layer here. So the layer which is just above in that liquid one is getting slightly slowed because it is sticking to a layer which is stationary, and the stationary layer is now getting slightly sped up because it is sticking to a fluid which is now moving. So the consequence is at an immediate next instant of time, the velocity will try to look something like this. That the layers which are very close to the interface will get slowed down and the bottom layers which are very close to the interface will start to move. And this is going to keep increasing. And now you can ask the question, how fast does this increase? Like if you quantify this region, that region is actually growing in time. So there was earlier a negligible region and that region is constantly growing in time. And you can answer the question, how rapidly does it grow? It grows as square root nu t. So you can imagine this in terms of evolution of velocity. You can imagine this also as evolution of vorticity. Because if you draw the vorticity field in each of these problems, the vorticity here at t equals 0 is a sheet, which means it's a singularity. And gradually that sheet is going to smoothen out. You have drawn a line of dye in a flow and the line is basically spreading out due to diffusion. So the line is going to get wider. So what I have drawn here on the red one is basically omega z, this is the y axis and the x axis is omega z. So gradually it is going to spread. And this is the functional form that you have here, which gives you a Gaussian function. So it exactly spreads in that manner. You can see. So for a Gaussian function, that is the width of the Gaussian. So the width of the Gaussian is basically increasing as square root nu t. So that picture, whether you think in terms of momentum transport or vorticity transport, is one and the same. So this particular problem is known as a mixing layer. And you can understand it exactly, or diffusion of a vortex sheet. So this diffusion of vortex sheet is known as a mixing layer, because you have two streams which are moving with different velocities. You don't need to have the bottom one be at rest. It just needs to be at a different velocity. And this is something which you see quite often in a lot of problems, whether it's engineering or environmental. You can have two streams coming and mixing together. So the two streams have come and they have merged, and now basically at the interface between the two fluids, you will have this momentum diffusion that is going to go around. Similarly, in an environmental problem, you can think of this where two rivers are coming and merging. So there are two streams of rivers which are merging and flowing downstream. And if you look at the interface where they are merging, you can clearly see two river streams which are there. And the interface will have a lot of curling up that is there. But that curling up is not something that we can explain based on this process. But the point is that there are these mixing processes that are happening between the two streams. When you have time, just go back and check the confluence of various rivers. In the Indian context, you have Alaknanda and Bhagirathi. If you look at the two river confluence, the picture, it is dramatic because the two rivers will visually give you a different picture. The color of the two streams are very different, and that has to do with the sediments that they are carrying and etc. So obviously that helps you visualize that there are two streams which come, and for a certain distance you will actually see that there is a distinct two streams which are flowing past, and they have different speeds. They are not moving at the same speed. You have to go a little further downstream, and the mixing has kind of homogenized the momentum as well as mass. So the color gets homogenized because of mixing of species and mixing of mass, and the momentum homogenization makes the current also more or less uniform. And this is also is also quite common in the Amazon, where you can look at the confluence of the two rios in Manaus, where you will see like a massive river, the Amazon forming, where the two rivers come in. I think one of them is Rio Negre and I forget the other one. So they will come and merge, and when you look at the merger of the two streams, you can see that the two are distinct. It's two streams which have coming and merging there, and the interface you can actually observe very clearly. So at the first level of understanding, it's a problem of understanding what is happening in a mixing layer problem. So you can take whatever you're learning. So there is obviously the impulsively pulled plate problem. There is a lot of neat approaches in terms of similarity variable, etc. that is going on. But the part which is actually the most important part in this whole thing is the fact that there is something known as a diffusion length scale or a viscous length scale. The distance over which viscous momentum is going to continuously keep increasing. So we discussed a problem which is like this, right? I didn't have the bottom stream, but you can imagine it's like this. So there is a u1, there is a u2. So at this location, if I choose my coordinate axis system to be like this, at y equals 0, the velocity is u is equal to u2 h of y plus u1 h of minus y. So now if you take the vorticity, that is going to be u2 delta of y, minus u2 delta of y, and then you are going to get plus u1 delta of y. So you will have an expression for velocity which is u2 when y, so this will be u2 when y is positive, and when y is negative it will pick up u1. So that's what the Heaviside function is doing. So when you take a derivative, the derivative of hy will be delta of y, vorticity is minus du dy, so I put a minus sign here, and the derivative of h of minus y will basically be minus delta of y, and then minus of minus will give you a plus. So you are going to get a minus u2 minus u1 delta of y. So you will have a vortex sheet that is like residing at that location. Okay. So this is how it's interesting to study more about unsteady flows, like what goes on in unsteady flows and how it behaves. Now, the problem that we did, which was an impulsively pulled plate problem, going back to that particular scenario, the impulsively pulled plate problem didn't have any inherent length scales or time scales in the problem, and so we got the similarity solution. Now, there are two kinds of modifications that you can do. So one could be that the plate is moving with a velocity, but it is not necessarily a constant velocity, but an oscillating plate. The other scenario could be the plate is moving with velocity u at t equals 0, but then there is a stationary top plate at the present at a distance h from the bottom plate. So now you can, before you solve these problems, it's interesting to actually think of what is going to happen. What is it that would you expect in this problem? So in the second problem, which is slightly harder to solve, we will first just qualitatively try to understand. You have already solved the problem of the single plate. So in the single plate, the velocities are going to basically keep increasing. Now, which means that there is a diffusion of momentum that is occurring, which goes as square root nu t. So after a certain time, which is of the order of h divided or h square divided by nu, because the viscous momentum diffusion is going on, it's basically percolating in the depth of the fluid. At some point there is a wall which is present there, right? So you have a bottom wall which is basically making the fluid layer keep on its moving, and eventually there is a time scale which is fixed by the height or the depth between the two plates. This has units of time, h square by nu. So you cannot have viscous diffusion go on arbitrarily for all time. Finally, if you wait long enough, you are going to get a profile which you have already done in class. That will be the linear profile. The linear profile, which is u is equal to u bar into 1 minus y by h. In class, we did u bar y by h because the top plate was moving. Here, the bottom plate is moving, so the velocity would approach the plane Couette velocity, which is 1 minus y by h. So you can solve the same problem. So you can take that exercise of doing this problem where you say that the top plate is stationary, the bottom plate starts to move at time t equals 0. This is y equals 0, this is y equals h. And you are now trying to solve, it's easier here to solve in the momentum equation. You are trying to solve this particular equation. So the boundary conditions here are u at y equals 0 for all non-zero time is going to be u bar, and u at y equals h for all time is going to be 0. The fluid velocity everywhere in the fluid at that initial time instant is also 0. Right? These are your boundary conditions. Now, you can't use similarity variable technique here because there is an inherent length scale in the problem. As I said, if you write down you can still do this exercise. You can still say that the fluid velocity is obeying an equation that is linear. The boundary conditions are linear, which is why I can write this now as a function of y, t, nu and h. This is the height, capital height. There is, did I introduce any small h anywhere? Oh, okay, thank you. Yeah, that's a bad notation. Yeah. So, okay. Yeah, this is not the Heaviside function. So, I think I will just do y equals small h. Yeah, this has no connection to the Heaviside function. This is just the gap between the plates. So, now you can solve this problem. I mean, you can solve this problem exactly. So, there are one method of solving this problem is using what is known as Laplace transform. So, what Laplace transform will do, that once you do a Laplace transform in time, you are going to get an equation which will be u of s minus u at, or rather this is u of y comma s, u of y comma 0 minus nu d square u hat dy square. Hat is basically your transform variable, whatever is your transform variable that you have in the problem. So, now then it becomes a second order differential equation which you can solve. This is a second order equation that you can solve. Your initial condition is known, and then once you have solved the second order differential equation subject to the boundary condition, these are your boundary condition, this is your initial condition. So, once you have solved the equation, you can then use this in order to find what would be your inverse transform. As I said, u of u bar from dimensional consideration is y, t, nu and h. Now, this is dimensionless, which means this also should be dimensionless. Now, we already know one combination of doing dimensionless thing, right, which is eta. So, it's y square by, or rather I think I called it as y by 2 root nu t. That is one dimensionless variable. Now, what is the other dimensionless variable? So, again you can do a Buckingham pi theorem and try to construct what the others are. Again, it's not a unique choice, you can use combinations, but the other one is going to be y by h. So, when you solve that Laplace transform problem, come back and do your inverse Laplace transform, you will finally get the solution with the boundary condition. So, I am just going to write that particular solution. It will be 1 minus y by h minus 2 by pi summation n equals 1 to infinity 1 by n exponential of n square pi square nu t by h square sine n pi y by h. This is the solution to that equation. Now, it's quite messy. It's not as neat as what we had earlier, but the part which you can focus and understand is that this is a summation over exponentials and sine. Now, nu is positive, T is obviously positive. H square is also, this is H again, help me just, yeah. H is also positive. So this is an exponential with a negative argument. So which means if you wait long enough, if you take the limit of t going to infinity, but or you can ask t being very large. Now what does t being large mean? You have to say large with respect to what? So you are saying that nu t by h square is actually very large, which means t is much larger than h square by nu, which is the point I was making earlier, that there is a time scale in the problem for momentum diffusion to spread over a distance that is comparable to the gap between the plates. So when you are looking at time scales which is much larger than that particular viscous time scale, these exponentials are all going to decay. And eventually, you are going to be left with a steady state solution which is 1 minus y by h. So now if you plot the solution between the two plates, obviously your earlier exercise from the class would give you the steady state profile. This is 1 minus y by h. You are plotting u divided by u bar. This is y equals 0, this is y equals h. But then the earlier profiles in time would not look like this. They are going to look so this is increasing time. So you have the steady state, this is the steady state profile, which is the linear profile, but for any any finite time, you will have a profile which will look this kind of take this kind of a curvilinear shape. So you have the momentum diffusion from the bottom plate all the way to the top plate. The top plate is held fixed, bottom plate is moving, and you achieve this steady state through viscous diffusion. So we had a question few lectures back, the fact that when we solved the Couette flow problem, we actually solved for an equation which was d square u dy square is equal to 0. This is what we solved in the plane Couette flow equation, which is to say that viscous force is 0. What is the role of viscosity? Because the plane Couette solution that we obtained in class was also a solution of the inviscid equation. This linear profile that you have, this is also a solution of the inviscid equation. But you will not be able to achieve this solution if you disregard viscosity. You can see this here now, that when you move one boundary and hold the other one fixed, we all know that you are going to get this linear plane Couette problem. But to achieve this linear plane Couette problem, you need viscosity because you will have momentum gradually diffusing from the bottom boundary to the closer to the top boundary, or whichever is differentially moving. You can also think of this in terms of vorticity, because the bottom plate is moving, which means there is a vortex sheet at the bottom. So this vortex sheet is going to keep spreading vorticity into the fluid until the entire fluid has constant vorticity, right? The vorticity for the steady state, omega z, for large time is going to approach plus u bar by h, right? If you take the derivative, minus du dy is basically my vorticity, so that will become plus u bar by h. So initially the fluid was at rest, which means there was no vorticity in the fluid in the gap. So omega z at t equals 0 was 0 everywhere other than at the bottom plate where you have introduced this vortex sheet. and this vortex sheet starts to percolate or diffuse into the fluid until in steady state the entire fluid has the same amount of vorticity. Just like a heat conduction problem. If you think of it like a heat conduction problem, it's exactly what you are doing here. You have introduced an initial heat flux and then it spreads and you achieve this linear temperature profile or a constant temperature gradient. So it's very important to think of the role that viscosity plays. So I'll just close by encouraging you to look at the problem that we have discussed several times so far. That is the problem of a rotating cylinder. So when you have a rotating cylinder, we know that there will be this paraboloid shape. We have worked all of these things out because the fluid is moving like a rigid body, u theta equals to omega times r, and this is a cylinder of radius a. We solve the inviscid equations. If you remember, what we did was we said let's look at steady state, axisymmetric motion, and then we have minus rho u theta square by r is equal to minus dou p dou r, and then in the axial direction dou p dou z is equal to minus rho g. We solved these two equations simultaneously and said that it was atmospheric pressure on the free surface, and we got the paraboloid shape, that z was going as r square. This was a pure inviscid calculation. But obviously, if you see this as an experiment, you start spinning the cylinder at some time. So if you are spinning the cylinder at some time, how did it manage to actually achieve this rigid body state if there is no viscous effects in the problem? Because the cylinder walls are moving in tangential direction. The fluid, if it was perfectly inviscid, should slip. So if I look at the top view, now instead of stack of books, you can think of it as concentric rings. So if this is the boundary is rotating with an angular velocity omega, which I have turned on at time t equals 0. So omega at r equals a for any non-zero time is, let's say, omega naught. Omega inside the fluid for t equals 0 is 0. Now if there was no viscosity, this surface can move with an angular velocity omega naught. The fluid which is adjacent to the surface need not move. It doesn't have any requirement to move. What makes it move is viscosity. Viscosity is what will make it move. And so it is going to spread angular momentum into the fluid until the entire fluid achieves a constant angular velocity. So there is a diffusion of vorticity or a diffusion of angular momentum until the entire fluid has constant angular velocity or constant vorticity, because the vorticity here, if z is the axis coming out, is going to be 2 omega naught in steady state. So again, limit of t much larger than a square by nu, just like the plane Couette problem. In the plane Couette problem, you had a time that was required for viscous diffusion to enter from one plate to the other plate. Here you have a confined cylinder, so the vorticity or angular momentum is diffusing and you get a time scale which is a square, the diameter of the cylinder, a square by nu. So when you are looking at time instants which are much larger than this, the entire thing is moving as a solid body. But solid body is the long time limit of the viscous problem. So you can try solving this. It's algebraically a little tedious, but it's something that you can give it a shot, that you can solve this problem, because now you will solve an equation for dou u theta dou theta is equal to nu 1 by r dou r of r dou u theta by dou r. I'm not sure. I think there would be an additional, I think those additional terms will most likely go to 0, because there is one term which is proportional to ur and there is one term which is proportional to dou theta of u theta. So whatever you have here as the Laplacian of u theta, that's the one which will be there. So you can solve this cylindrical diffusion equation and you will find that there will be a u theta which is subject to the boundary condition that u theta at r equals a for all time is omega naught a, u theta for r for all r at t equals 0 is equal to 0. So if you solve with this, you would obtain that it will eventually achieve steady state. You just have to wait long enough. Okay, fine. So the part that is still left is going to the other problem where there is an inherent time scale, which is an oscillating plate. Because now you don't have a length scale that is there in the problem, but you have definitely a time scale that would be there in the problem. So you will have to think in terms of that there is going to be a length here which you can construct in terms of nu by omega. Earlier there was no length scale, but now you can construct a length scale given this frequency. So which is going to now make you think that what is going to happen in this distance which scales as omega by nu. Can viscous diffusion percolate forever? Because in the problem of the impulsively pulled plate, the profile basically keeps getting flatter and flatter and momentum keeps diffusing further and further away from the plate. But now I have a length scale which is given by the frequency of oscillation, which is square root omega by nu. So that's going to act as a depth over which viscosity can penetrate and no further because of the nature of the oscillation. So we will do that in next lecture.